Hey there, folks. Today's topic is the fundamental theorem of algebra. So we've already talked about the fundamental theorem. We're just now kind of putting all the pieces together to sort of formalize how the theorem works. So remember, the fundamental theorem says that if you have whatever the highest exponent, or what we call the degree of a polynomial is, that's how many zeros you should have. So let's do a theorem here. So if f is a polynomial function with degree n, comma, then f has exactly n zeros. So in other words, if I have an x to the fifth, there should be five of those zeros. Now the problem is sometimes those zeros, they might have multiplicities. So remember our multiplicity conversation that we had earlier in the unit. But sometimes those zeros are imaginary. They don't show up if you were to graph them, but they still exist as zeros. So usually we have to do this algebraically to try to find out where all those zeros are. So let's do a quick review of a couple of things. Let's start off with x squared subtract 16. You should be able to factor that fairly quickly. How'd you do? Hopefully you recognize this turns out to be x plus 4, x minus 4. We have a couple of different methods that we call it. We call this dopes. That's the difference of perfect squares. And then we also call these things conjugates. Conjugates are a very powerful advanced math move where you could take something that it kills off the x in the middle. I'll just leave it at that for now. I've talked about conjugates a lot in this class. So I want to point out today is that even though this isn't going to be technically dopes, you can still factor this kind of like dopes when this isn't a perfect square. So let's take something like x squared subtract 15. Now, how did you come up with 4 and 4? Well, that's because 4 times 4 makes the 16. Now, we needed 1 to be plus and 1 to be minus, not only to create the negative, but to make sure that when we distribute, one would be a negative 4x and the other one would be a positive 4x. So I want to think about this the same way, except I just can't, my two numbers aren't going to be as nice. What two numbers multiply to make 15? Hopefully you're not saying 7.5 and 7.5 because, sorry, I said what two numbers multiply. I can't just pick any two numbers, like 3 and 5 won't work, because if I did 3 and 5, then the middle piece wouldn't cancel out. It would add up to either a 2 or an 8 in the middle. So we have to make sure these two numbers are the same but opposite. So what number times itself would give me a 15? Well, it's kind of sneaky, but once you see it, it makes sense. I can use root 15. So x plus root 15, x minus root 15. So when I go x times x, that's x squared, then I would get a negative root 15x and then a positive root 15x, so that adds to 0. Positive times a negative is a negative. Root 15 times root 15 ends up being 15. All right, so that's dopes. Dopes, we can even do dopes even though it's not technically a perfect square. I don't know what the actual name of this is. I don't know if can't call it dopes anymore. Can't call it difference of perfect squares. Anyway, we also talked about the sum of perfect squares. So let's say I tried to do x squared plus 16. Now, according to dopes, we couldn't do this because let's say I needed one to be positive, one to be negative, they have to be opposite. They have to be conjugates to add up to 0 in the middle. I want there to be 0 x's. So if I used 4 and 4, that would make 16, but it wouldn't add up to 0. It'd add up to 8 x's in the middle. If I use -4 and -4, it would still make a 16, but it would add up to -8 in the middle. So I got to make sure that these are x plus and x minus. I've got to make sure they're conjugates, otherwise they won't cancel out in the middle. Well, I know that 4 times 4 makes 16, but if I put a 4 here and a 4 here, that would make a -16. So what have we dealt with that if you had two of them, in other words, if it became squared, it would change the sign? Well, hopefully you thought of i's. 4i and -4i. Now watch what happens when I distribute this. X times x is x squared. X times -4i is -4ix. 4i times x is positive 4ix. And then positive 4 times -4 is -16. I times I is I squared. We talked about this when we did complex operations on complex numbers. What happens when you square I squared, when you square I, it changes the sign. So now I've got -4ix plus 4ix. Those cancel out. And then I have x squared, and this -16 became a positive 16. So it does actually distribute out. Maybe I should box. I think I'm going to box these in. So I call these dopes, difference of perfect squares. I don't have a great name for the other ones, so I just call them SOAPs, sum of perfect squares. Yeah. Sum of perfect squares. So when you're doing a sum of perfect squares, what are you going to need? You're going to need an imaginary number along the way. So let me give you one. Let's see if you can do both moves at once. Yours is going to be x squared plus 15. Pause it, give it a try. All right, so hopefully you noticed that it was a sum, so you're going to need some i's, and you also notice that this is not a perfect square, so we're going to need some weird roots, and then your answer should have been x plus, and we like to put the I in front of the root, so if you put it after, I understand, but usually you want to put it in front. X plus I root 3 and x minus, oh man, I didn't say in the box. X minus, what do you think? All right, so we might need these moves. These are just added to our arsenal, our toolkit of how to factor things. So right now we've got, if you're already factored, we've got factoring, we've got quadratic formula, we've got dopes, we've got solving, we've got factor out, and we've got, what's that other one called? Oh, weird. Oh, that's what we're going to do right here. We're going to do a weird. Now we can add SOAPs to the mix because we've now introduced these things called imaginary numbers. All right, so find all the zeros. So I'm going to underline that. I want to find the zeros of x to the fourth minus x squared minus 20. Now, if you want to do the rational zero test, feel free. If you want to make the little list of all the possible numbers and go from there, you can do that. That'll work. I'm going to notice that this is a certain type of factoring that we did back in 2.3. So this is not, I can't just do regular factoring. I call this weird factoring, and I recognized it because there was 3 terms and it went 4, 2, none. Just like if it went 6, 3, none, or 10, 5, none, or 150 and none. These exponents, if this is twice what this is and then there isn't one there, I can factor this doing weird. So I'm going to do regular x factoring. First term times last term, 1 times -20 is -20. I'm trying to build a -1, so that would be a -5 and a +4. So I can factor this into x subtract 5 and x plus 4, except to make this into an x to the fourth and to add them up to be an x squared, these have to have squareds on them. Okay, so now from here, I want to find the zeros, which means I need to ZPP. Well, there's 2 ways you can do it from here. You can set these equal to 0. You can keep factoring if you want. So in other words, I can factor this and I can factor this. We just learned how to factor when it's a dopes without a perfect square. So I could factor this into x plus root 5, x minus root 5. And we just learned how to factor this when you have a sum. Sum means you're going to need some imaginaries, and 4 is a nice perfect square. So I'm going to have x plus 2i and x minus 2i. And then this is going to equal 0 because we're trying to find the 0. So now I would ZPP each one of these, and we would get x equals, when I bump this over, that becomes negative root 5. When I bump this over, that becomes positive root 5. When I bump that over, that becomes negative 2i. When I bump that over, that becomes positive 2i. Now, let's say you didn't think of that. Let's say you tried to do ZPP right off the bat. That's fine. You're still going to get the same result. So I'm going to now take this, and I'm just going to ZPP right away. Because I only have one x, that means that this is fairly easy to solve. So I can break this and bust it equal to 0, and I can take this and bust it equal to 0. Now I can solve these. So I'm going to bump over the 5. X squared equals 5. Who's keeping x from being by himself? Squared. So what kills squared? Our good friend square root, but square root is on fire. We don't need no water. We just need a plus or minus. Same thing here. I'm going to bump over the 4. X squared equals negative 4. Who's keeping x from being by himself? Squared. Square root is on fire. We don't need no water. We just need a plus or minus. And then what's the square root of 4 is 2. So what's the square root of negative 4 would be 2i. And you'll notice that these are the exact same list of zeros. X equals plus or minus root 5. There's minus root 5. There's plus root 5. X equals plus or minus 2i. Minus 2i plus 2i. All right, now the ultimate scenario. So let's go through, and we're going to try to just look at our function and try to apply one of our moves. Find all zeros of f of x equals blah. So what should you try to do first? Hopefully your math voice said try to factor. So I'm going to try to factor this thing. So 2 times 17 is 34. And I'm trying to make a negative 8. That's 34 is, I think that's only 2 and 17. Yeah, 2 and 17 both are prime, so there's no other way to break this down. Factoring does not work. When factoring doesn't work, what will work? The quadratic formula. So now I'm going to jump to the quadratic formula. X equals negative b, so that would be 8 because it's already negative, plus or minus the square root of b squared minus 4 times a times c, all getting square rooted, over 2a. We do not want to turn this into a decimal. We want to clean it up nicely. So we're going to start with the stuff that's under the root. I would need my calculator here. So I'm going to type in everything after the root. So I'm going to start with the negative 8. Notice I didn't put the root in because I'm trying to calculate what's under the root, not the root itself. We get negative 72. So I've got 8 plus or minus the square root of negative 72 over 2 times 2 is 4. Negative 72 is something that we can try to clean up. Are there any perfect squares? Well, right away there's an I. So I'm going to break this up into negative 1 times. Is there a perfect square that goes into 72? 72 divided by 4, yes. 72 divided by 9, yes. 72 divided by 16, no. 72 divided by 25, I'm not even going to do that one. I know that one won't work. Why didn't I stop at 4? Because there's a perfect square that goes into 18. That means something else will work better. Why didn't I stop at 9? Because there's a perfect square that goes into 8, 4. So that knows I know I can do better. 16 didn't work because it had a decimal. 36, because 2 is prime and no perfect square goes into it besides 1, then I know that's my best combination. So 36 times 2. All of this is getting square rooted. So what would our cleanup look like? 8 plus or minus. All right, so I'm going to take the nicest thing out first. So the 36 square rooted becomes a 6. The square root of negative 1 is I, and then 2 is left in jail, over 4. And then what do you notice? Don't forget that you can reduce fractions still. 8, 6, and 4 are all divisible by 2. So we get x equals 4 plus or minus 3I square root of 2 over 2. So I go through my list, x to the 4th. I can go right down to the bottom. I can't factor this. It's not already factored. It's not dopes. It's not factor by parts because there's 5 terms. So I go to my higher exponents. There's nothing I can factor out, and this isn't weird. So when everything else fails you, you're stuck doing the rational zero test. So let's start off by trying to figure out all the possible rational zeros. So RZT. That'd be all the factors of 36 over all the factors of 1. So that's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 5 doesn't work, 6, plus or minus, okay, so 6 goes with 6, so now I just need to match these up. 4 would go with 9, 3 would go with 12, 2 would go with 18, and 1 would go with 36. And these are all over factors of 1 or 1. So that's easy. There's my list. I don't really have to rewrite it because everything divided by 1 is itself. So my numerator is my list. So I want to guess and check here. I usually start with the easiest ones. I'm going to start with 1. My coefficients are 1, 1, 16, 18, negative 36. 1 drops, that's 1, that's 2. Then you multiply, that's 2, that's 18. Then you multiply, that's 18. That's 36. Then I multiply, that's A, all right. That's 36. That's 0. So, smiley face here. Circle that. That's one of my zeros. Okay, so this was next to the 4th. I've broken it down once. That means this is still a next to the 3rd, so I've got to find another one that works. I should probably try negative 1. I could try 1 again. I'm going to try 2. Let's try 2. So 2, and now I'm breaking 2 into these, 1, 2, 18, and 36. 1 drops, that's 2, that's 4, that's 8, that's 26, that's 52. No good. 2 is out. 2 didn't work. So I'm going to try something else. I'm going to try negative 2. This time I'm going to go back to this line here. Don't go all the way back to the original because then you got to keep checking. So I'm going to go back to 1, 2, 18, and 36. 1 drops, that's 1 mult, that's negative 2, that's 0, that's 0, that's 18, that's negative 36. Yay, we got a 0 there. So how many zeros are we supposed to have? We're supposed to have 4. How many have we found? 2. So we've got a little bit more work to do. This was an x to the 4th. We broke it down once, so this was an x to the 3rd. We broke it down again, so this is an x squared. X squared plus 18. Now from here, I'm noticing this is SOAPs. You can go back up here and you can try to factor, or you can just solve doing ZPP, and that's what I'm going to do. I'm just going to set this equal to 0. X squared equals negative 18. I'm running out of room, which means square root, square root, square root is on file. We don't need no water. We just need a plus or minus. So plus or minus the square root of negative 18. All right, plus or minus. So I'm going to take out the negative. Is there a perfect square that goes into 18? Yes, 9 does. Goes into there twice. So I get plus or minus. The 9 escapes and becomes a 3. The negative 1 escapes and becomes an I. The 2 is left in jail. So now I want to make a list of all my zeros. Yeah, I wish I would have picked a different color. Let's go with a nice dark blue. So my zeros are 1, -2, and then plus or minus 3I root 2. 1, -2, plus or minus 3I root 2. All right, so basically, we have now just put everything together. That's the idea of today's notes, is now we've added some imaginaries to our regular factoring moves that we've already talked about. We've talked about the rational zero test, and we've already talked about how to do quadratics and factoring. We've just put it all together into one now overall package called the fundamental theorem of algebra. So all those factoring moves are still applying. You just might get some imaginaries along the way. Good luck.